My name is Dan Stieler, and I work for a company called PowerFilm Solar. We make small electronic component solar panels and some larger systems as well. Today I'm here to talk with you about solar energy harvesting for maintenance-free sensor deployment. So first of all, I wanted to get an idea of talk a little bit about what energy harvesting is and where the energy comes from. So energy harvesting is typically known as collecting and using ambient energy from the world around you. And so that could be in the form of light collected by solar energy, motion collected with piezoelectrics, or electrodynamic systems like regenerative braking. Other electrodynamic systems could be something like a hydroelectric dam, a wind turbine, a tidal type system. Or even something like a audio or acoustic generator. Heat through a thermoelectric generator, and then radio frequency energy through something that collects electromagnetic waves. And so the question is the energy really free? Well, the answer is sometimes. And hopefully what your system's set up to do is to collect energy that is really free. And so the difference between the free energy and not free energy is energy that would be normally thought of as either waste or underutilized energy would be free energy. Energy that actually comes from the system itself would be not free energy. And so if the energy is external to the system, like light from the sun or light that's generated in the room, or electromagnetic waves created by a wireless router or a cell phone tower, or heat that's generated by a process that you don't really want or don't really use, then it would be more or less free energy, because it's something that's unwanted, or it's there all the time. It's not being totally used up, and it comes from outside your system. If the energy is actually internal to your system, so say you have somebody who's wearing a backpack, and as the backpack bounces up and down, it collects energy from the motion of the backpack. Well, the backpack bouncing up and down is actually caused by you walking, and in order to create that energy, you're going to have to work a little bit harder to make it bounce up and down and to make the harvester itself move and generate energy. And so that energy is not free anymore. I mean, you're going to have to eat some more food, you're going to have to do something to increase your calorie count in order to produce that energy. I mean, it could also be in the form of heat. If you have something like a heat sensor on your body, or a heat generator on your body, or a thermoelectric generator, it's going to actually cool down your body. And so that's great if it's really hot out, or if you're in a situation where your body needs to be cooled. But sometimes that's not good, because if it takes too much heat away from your body, then you end up having to use more energy again to keep your body warm. So why would you want to add energy harvesting to a system? There's a number of advantages really to adding energy harvesting to the system. First of all, and probably the most important thing, is extending the system life. And so it may be that without an energy harvesting solution, your battery lasts, say it's a battery powered system, lasts for 3-4 years. If you add some sort of energy harvesting, it could easily be 10 plus years that the system operates. It reduces your cost of ownership, because you don't have the maintenance required to change batteries if it's a battery-powered system. And so, for example, if you had, say, a battery, a coin cell battery operating device, the battery itself may be 10-20 cents, but the maintenance to replace it, say it takes 2 minutes to replace the battery, the sensors are really easily available, somebody can walk by and do them pretty quickly. So for a 2-minute battery change, that's going to be roughly 80 cents or so. So almost every time you change a battery on a system that's readily available, it's going to cost you $1. And you have to make sure you have the labor available to do that. If it's something that's a more remote system, say you have to drive a few miles or something to get to a place where you're monitoring something, you could easily be spending $5, $10, $20 or more on a battery change for a system. And so lowering that cost of ownership is one thing that energy harvesting can do for you. It also, by reducing the amount of maintenance, if you're in an environment like a class 1 hazardous environment, you're not going to have to worry about battery changes, which is a big deal because there's a lot of special considerations that have to take place anytime you're opening up a power source or doing maintenance on a power source in an environment like that. You can reduce cost of installation because you don't have to have a hardwired system to be basically viable for long periods of time or forever. You don't have to have an electrician come in and wire in the system. You can operate off a energy harvesting power source. Operating off one of these power sources also makes installation very flexible. It could be as simple as a solution that you have with a built-in circuit board, built-in energy harvesting device, your built-in low-power electronics, and you could have it as a peel and stick application, so they can just stick it on their wall, or they can stick it on a machine, or put it wherever they want to use it. So it makes installation, maintenance very simple, and for a long life product. And all these things, including data reliability and uptime, all roll into customer satisfaction. These things also really enable a large number of devices. So in 2020, if you look at the plot on the right, something like 30 billion IoT type devices, connected devices. By 2025, they're predicting it's going to be something like 75 billion. And so in order to really make getting large number of devices viable, especially in small areas or for individual companies or groups, you really need something that's self-sustaining. Some of the applications we see for energy harvesting are things like Bluetooth low energy beacons and tags. These tags could be something that's in say a retail store. They're a point of sale display. The point of sale display may push coupons to a person as they walk by when their cell phone comes into range, or do things like that. Also, a Bluetooth low energy beacon or tag may be tracking where assets are at on a manufacturing floor or in a manufacturing line or warehouse. Wireless gateways or edge devices, being able to power these and install them in places that are most convenient around a place without having to run power for the electricity can be a very attractive thing. We've had customers that have done things like this for retail stores where they're putting in gateway type systems to track where beacons or tags are in the store, and doing it in a remote fashion by putting them up near lights to power them. Environmental monitoring or predictive maintenance, looking at vibrations to determine what a failure is an example of a wireless sensor. One of the applications that I had heard about in the past was where a sensor was put on a rail car system, and this was monitoring vibrations on the rail car, and they could look at those vibration data and say, okay, this section of track is bad and needs to be replaced, or this wheel or truck on the train itself needs to be replaced or is coming towards the end of its life, so let's get this in to the depot to have the bearings replaced before we have a problem out on the tracks. Things like electronic shelf labels, again, in a retail setting, make updating pricing very simple. Wearables, things for monitoring health or position tracking. We've done a few wearables for animals in the past. The bottom right-hand corner here actually shows a rhino with a solar wearable around its ankle for tracking where the rhino's at, where its location is, what its habits are. Done similar things for things like the painted dog and the camels. Telematics would be another area, especially telematics and things. Or one example of telematics is in the semi-tractor trailer or transportation business, looking at compliance items. Are all the lights working on my trailer? Or are my doors opened or closed? Is the refrigeration temperature at the right level, keeping the product I'm transporting good? Are the tire pressures on the truck or trailer fine? Where's the product located at right now? Those types of things. Field or herd monitoring, having a tag on a cow that's looking at its temperature and can report back temperature, position. You can tell, is the cow going and eating? Is it drinking? Is the temperature normal? Do I need to get a vet out there because something's not quite right or the temperature's getting higher, and try to take care of the animal before it gets really sick? In field monitoring, looking at soil moisture levels, light levels, nutrients in the soil, all those types of things. Smart locks, the other example, the picture on this page is a bike lock in the upper right-hand corner. That lock would tell you if somebody's tampering with your bike, what the location of the bike is. It provides crash detection. If you had a crash, it would call somebody and let them know that you had crashed. Automatic locking and unlocking within proximity. And then other low-power electronics, powering things that use things like Bluetooth low-energy radios, Zigbee radios, LoRa, cellular, all those types of things. So there's many applications for energy harvesting. So the basic system components for an energy harvesting device, and we're going to look at solar specifically, is having some kind of energy generator. So in our case, a solar cell. The solar cell is going to be able to create power in the microwatt to watt range, typically when you think about energy harvesting. The energy harvesting circuit itself its point is to take and match the voltage of the battery or match the output of the solar panel, the ideal output of the solar panel, so where it operates at maximum power, to the battery, and convert the power from the solar to the battery in an ultra high efficiency manner to collect every microwatt of power that's generated. And then storage elements. The storage element could be a battery or capacitor, and there's things that you need to take into account when you're designing with a battery or capacitor. Make sure that your capacities are at the right level. Choose high quality batteries. If the storage element itself says that it has a certain capacity, make sure and check those things. Sometimes storage elements don't actually have the capacity that's advertised. We've seen a range from where you'd have a very high quality brand that puts out exactly or a little more than what it's rated for, versus a no-name brand that may only put out 50% of the rating. They're both rated for the same thing, but you only get half the power from one versus the other. So understanding what you're using for a storage element is important. Also understanding, how much am I going to discharge it? By adding energy harvesting, your depth of discharge on a battery, your storage element can go down significantly. If you take lithium iron phosphate, for example, if you're operating that battery between 85 and 95%, you may get 15,000 cycles out of the battery. If you're operating that battery down to 50%, you may get 2,500 cycles from the battery. If you're operating the battery down to 85% or down to 15% of total capacity, you may only get 500 cycles from the battery. So understanding what you need for a cycle life from the battery and how it's going to react depending on depth of discharge is important. And then when we're talking about using things like radios, the radios typically have a high peak current when they're transmitting. And so with those high peak currents, those levels are frequently not sustainable for the small coin cell type batteries or smaller batteries, pouch lithium batteries that you would put in a IoT sensor or small device like that you'd pair with energy harvesting. And so you want to make sure that the battery is big enough to be able to supply those currents, but still small enough to meet your form factor, weight requirements, all that kind of stuff. And the good thing is when you move into doing designing with radios, a battery can output for a very short period of time those higher currents and then relax back down, and you'll still get a reasonable lifetime or reasonable number of watt hours out of the battery as compared to if it was continuous draw. So if you had a continuous 30 milliamp draw on a coin cell battery, its capacity may be, say, 1 milliamp hour. But if you only have that for short spurts when you're doing something like a Bluetooth low energy radio transmission, you may be able to get by with that for short spurts and still get 10, 12 milliamp hours out of the same battery. And so nature's kind to us in that way, in that the batteries have a relaxation time, and we can use the radios that are higher current with a typical battery and still get reasonable output. The final thing is the low power electronics that you're going to put with the energy harvesting system. So a few types of energy harvesters again. Thermoelectric, which is a heat harvester, piezoelectric or electrodynamic, which is motion, radio frequency is the electromagnetic radio waves, and solar is light. When you look at it, thermoelectric and the solar tend to be the ones that have a wider range, going up to higher powers. They're also cyclic and predictable in the variability. So for example, with solar, you know that the sun's going to come up, and you can predict, kind of based on previous history outside, you know, how often it's going to be a cloudy day, what's the total amount of power available from the sun going to be for a month, that kind of stuff. If you have solar indoors, again, it's very predictable. You know, the lights are going to come on, they're going to be on for 8 or 10 hours during the workday, and then they're going to go off. And so you have kind of a predictable, reliable, cyclical power source. Lifetime of the different things, it varies, but things like the radio frequency devices and the solar tend to have very long lives, 20 plus years typically. And that's because, like in solar's case, a lot of the solar is the same solar that you would find rated for outdoor use or permanent use on a utility scale thing that's being used for an IoT type application. Minor modifications to things like encapsulations and how it's constructed for indoor versus outdoor use, but still, you know, the base material is going to produce power at 20 plus years, no problem. The investment, heat and motion are relatively expensive. Forms of energy harvesting equipment. Radio frequency is very cheap. It typically is just kind of an antenna that's paired with your energy harvesting integrated circuit. Solar's kind of middle of the road. And then from a size perspective, the piezoelectrics are probably the smallest harvesters. The solar and the radio frequency are kind of medium to large, depending on the amount of power you need. Solar specifically, the area or the size of its footprint really scales relatively linear with the amount of power that's required from an application. So the lower power your application, the smaller area it's going to be. Higher power, you know, higher area. Okay, so most of the rest of the presentation, we're going to spend some time talking about light and solar and solar cell efficiency. And so the first thing I want to point out, and then we'll support as we go on through the presentation, is that solar cell efficiency doesn't really tell the whole story, especially when you're talking about indoors. Efficiencies are typically quoted for panels under 1,000 watt meter squared illumination at 25 degrees C, and it's based on the outdoor sunlight spectrum. When you move to powering energy harvesting and powering an indoor device, indoor light sources don't match outdoor sun really at all. So it's very different. The quantum efficiency of higher efficiency solar cells is not a good match, and that's because of the cell matching to indoor lighting. And parasitic leakage at low light intensities can cause problems and really reduce the performance of your solar cell at low light intensities. So briefly, we'll talk about measuring light. If you're going to start to prototype for an application, you need to know what do you think your normal lighting scenario is going to be. And so you can do that by using your eye. You can do that by using a lux meter. A lot of times we'll have people who start out saying, well, it looks like it's really bright in the area I'm using. Well, it turns out your eye is not a very good detector of light intensity, and that's because the eye itself has an iris that adjusts automatically to light intensity all the time. Now, your eye is pretty amazing. It has a 1,000,000,000 to 1 contrast ratio, but it only really has 1,000 to 1 dynamic contrast ratio. So what that means is you can only see 1,000 different variations in contrast, basically, in any one scenario. And so when I walk into a room that's at 500 lux, the room looks bright, my eye's adjusted, it looks like there's plenty of light there. When I walk outside and it's cloudy, this may be 25,000 lux instead of 500 lux, but it may look, relatively close to the same for my eye. And so that's a big difference in actual light, or big difference in power available at something like a solar cell. Also, the eye has a pretty limited spectral response when compared to solar. And so we'll get into that in a little bit. The units of lux meters are easily available. They're probably the most frequent go-to type measurement device for light that you'll find. They're inexpensive. Oftentimes they're not very accurate or well calibrated, but that's okay. They can give you a general idea how much light is there. In the upper right-hand corner, you can see the lux meter response. It's really confined to the visual spectrum, and it's a pretty Gaussian distribution. In the bottom right-hand corner in this slide, you can see there's the different quantum efficiencies of different types of solar cells. The green and the purple lines are some of your higher efficiency solar cells, your crystalline silicon and gallium arsenide. The other grouping of lines, red, blue, and brown, are things like amorphous silicon, multicrystalline silicon, and dye-sensitized. And you can see that the quantum efficiency, which is the efficiency that you can absorb a photon and convert it to electricity for a specific wavelength of light, is much narrower for some of those devices, but it's actually well matched in the 400 to 650 range to what indoor lighting would be. All right, so on this slide, we're going to learn a little bit about what kind of intensity is available or what kind of power is available for different lighting scenarios with an amorphous silicon cell. On the right-hand side, you'll see a plot that is really based on an indoor amorphous silicon panel, and it shows at various lighting scenarios what you would expect for power generation. On the left-hand side is an outdoor amorphous silicon panel and what you'd expect for power generation on different lighting scenarios. You can see at about 400 lux, there's a little bit of difference between the two. The indoor optimized panels will get somewhere around 12, 13 microwatts per centimeter squared, while an outdoor optimized panel may be more like 9 or 10. And so you could use these two plots to kind of size or get an idea of how much power or how much area you would need from a solar cell, depending on your power requirements and what the lighting is. They're also kind of handy because they can show you what typical light might be available for a different type of lighting environment. So for example, a windowless room may be 400 lux. Something near a window in a room may be 1,000 lux. Let's talk a little bit about the light source differences, or give you a visual here on what the differences are between light sources. The AM 1.5 solar spectrum is shown on the left. You can see that the gray areas in the spectrum are infrared. Those are areas that we don't see in light that is indoors. Most of our high efficiency light sources, with the exception of incandescent bulbs, don't have much infrared. If you look in the upper right-hand corner, you can see the different light sources and what their spectrums look like. You can see that the incandescent, the blue line, does have a fair amount of infrared. The black line is the overlaid, is actually what your lux meter response is from previous slides. And you can see the other three lines, the red, the green, and the purple, are your high efficiency light sources that are mostly within that measuring area of the lux meter, and certainly within the certainly within the quantum efficiency of the amorphous silicon solar cells. So comparing the amount of solar, or comparing the performance of the different solar technologies, you can see here that the amorphous silicon will produce more power per centimeter squared than the other technologies that are tested. Now there's some variation, especially in this crystalline silicon, but generally on the small panels that you would buy for a small IoT application that's a couple square centimeters, this is what you'll find. With the SIGS panels, they perform poorly because they have a lot of parasitic leakage, and so in low light levels, that parasitic leakage takes over and they don't perform so well. The crystalline silicon have issues because they're high efficiency, but they are set up. They get that high efficiency from being able to absorb into the infrared. That's not available from the higher efficiency light sources. And when you look at these cells, they are built on large wafers and then cut up into really small pieces and wired together to get a small IoT type panel. And the cutting creates parasitic leakage paths, and the wiring increases the total amount of area of the panel, which then correspondingly decreases the areal efficiency. And efficiency, when you're talking solar, is really the amount of power per area. That's how it's measured. The amorphous silicon has an advantage because it's a low leakage technology, so it works well indoor like that. The cells that we make are all printed. They're monolithically interconnected, and so they're all on one piece of plastic, so you don't have to worry about wiring together and losing a great deal of space due to that wiring concept. And their quantum efficiency is well matched to indoor lighting. Triple junction gallium arsenide, which would be the highest efficiency of any of the materials, maybe at 30% outdoors, but it gets limited by one of the junctions that really is focused on absorbing infrared light when you move indoors. Here's just an example of the amorphous silicon and optimized for indoor versus optimized for outdoor. You can see that the cells that were optimized for indoor have about a 30% higher open circuit voltage than the cells that were optimized for outdoor. So when you're collecting solar energy with an energy harvesting IC, what the IC is supposed to do is it's supposed to match the maximum power point of your solar cell to the battery. And so it does this. It does this by looking at a family of curves. Every solar cell has a family of IV curves, or current versus voltage curves, that occur at different light intensities. You can see 3 of them here at 200, 400, and 1,000 lux. And these energy harvesting ICs try to find the maximum power point and move the maximum of power into your battery. So there's 3 systems that are used to do that. One is called a fixed set point, where you set a specific voltage in your IC. That's depicted by the yellow line, and you can see how that doesn't necessarily track really well with the actual maximum power point of the cell, but can work well if you know what your lighting environment is and it's fairly stable. Then the other 2 are ratio power point tracking and actual maximum power point tracking. The ratio power point tracking looks at the open circuit voltage and sets its voltage based on a ratio of open circuit to where it thinks the power points should be. And you can see if it's set up right, that fits very well and can be close to what an actual maximum power point tracker would find. Amorphous silicon thin film solutions are ideal for this type of application. We make them using a high throughput roll-to-roll process. They can be optimized for both indoor and outdoor light performance and are highly customizable. They can be as thin as 6 mil and have a very high specific power density. If weight is important, and a flexible package like this on plastic, you can get about 170 microwatts per gram versus about 15 microwatts per gram that you would get from a glass panel. They're very conformable. You can conform them around about a 1/2 inch radius. They're compatible with SMT processing. You can do things like a conductive epoxy or put in flex connectors into your SMT board that the panel will plug right into. Their temperature range can be anywhere from 65C to 85C, depending on the laminate chosen. And they're just an extremely durable product made here in the US. Finally, if you want to get started with something like this, visit our website, PowerFilmSolar.com. We have a number of standard products in the electronic component panel offering. We have development kits with various energy harvesters and Bluetooth radios. And we have a custom solar panel design tool to help guide you through the process of designing a panel that fits your application. That's also what we do day in, day out. So if you want help, please give us a call. We'll work with you to understand your power budget, your power requirements, and design and build a panel that is right for you. Please visit our technical blog to learn more about solar and energy harvesting with solar. And just feel free to give us a call. Thank you.